very important classification associated with the system is the causality. Okay, so a system is said to be causal if the output at any time depends only on the values of the input at the present time and in the past. Okay, and such systems are also called realizable systems. So practically, you cannot have a system that can anticipate the future. Okay, so that makes more sense. So you see, for example, an automobile which is being driven by a driver, the motion of such an automobile is causal, okay, because it only takes the inputs, the present time input or any past settings that the driver has made in an automobile, and such motion can be the output of the system can be described as causal, okay. So you see, such systems they're often referred to as being non-anticipative. So the system output does not anticipate the future values of the input. Okay, so for example, again, the automobile cannot predict, it cannot anticipate what the driver is going to give the input in the future. Okay, so the motion is only depending of on the present input and on any previous settings. Okay, so it's a causal system. Then consequently, formally, the definition of causality for a discrete time and continuous time system is described by this statement. So, if you have two inputs to a causal system, and they're identical up to some point in time t naught or n naught, the corresponding outputs must also be equal up to the same time. So, what it means is that suppose you have two inputs, let's call them x1 of n, okay, which is identically equal to let's call this another input x2 of n. So x1 and x2 are identically equal. They might be different, okay, but they are identical up to a certain range in time. Call it, let's say when n is less than equal to n naught, okay. So you have a discrete time system, and we are going to apply two inputs, okay, and they are identical up until so long when n is less than or equal to n naught, okay. Then causality implies that the outputs corresponding to x1 is y1, corresponding to x2 is y2, will be identically equal, will also be identically equal up until the same range, okay. So y1n and y2n are identically equal up to the same range, okay. I mean this so long they are identical, the system cannot anticipate what the output is going to be, or how the inputs are going to change. So the interpretation is simple. You see, x1 and x2 might be different, okay, but so long they are identical, okay, up to a certain time instant n naught, okay, the outputs will be identical. That means what happens beyond n naught is not being anticipated by the system, right? So the systems, the outputs are also identically equal. So what happens beyond n naught cannot be predicted by the system. So therefore, y1n and y2n will be identically equal. Okay, so this formulates the this is a formal definition of the causal systems. Okay, system cannot anticipate what is going to come in the future. So this is a formal definition of causality. Causality. All right. Now, so as an example, the RC circuit that we have considered before, for example, is causal. You see the capacitor. This, if you consider this as a voltage and the input is the current, then since the capacitor voltage responds only to the present and the past values of the source voltage, you see you have the past up until the present time t, which is being taken by the argument of the voltage. This system is also causal, okay. It does not require any future values of the input, okay. So it's again causal. Now, however, for example, systems which is being defined by, this is a discrete time system, which is being defined by, so by x of n minus by this difference equation. So to compute the output, you require the present sample and you require a future sample. Okay, for example, if I need to compute y of 3, let's say. Then I need the present sample of the input, and I need to take a difference of this sample from one that is that's in the future. Okay, so one sample that is that is beyond 3 4. Okay, so I need a future sample, and to compute the output at 3 I need x4. Okay, whatever the value of the input is beyond 3, so that means at the present time index you require an input that is beyond the present time index, which means future. This system is non-causal. Okay, this is although this system is supposed to have memory. Okay, I mean this system uh, the system requires some sort of storage. It could be a recorded data if you have to talk about practicality of the system. If you have a recorded data, then you can have a future values as well. Okay, I mean if you have a timeline or you have discrete time indices and you have recordings. Okay, so this is n1 and 2 dot 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 dot, dot whatever. I mean let's say you have 10 samples. Okay, but this is a recording. So if you have to compute, for example, y of 2, then this is x2 minus x3. So you have this record. If the data is recorded and uh, it's not the sequence that is coming out, or you're doing the sampling at instantaneously. Well, yes, then you might realize this system. But non-causal signal processing is only possible on recorded data. You cannot realize such a system in practice. Okay, so anyways, over here as well. I mean, this is a continuous time system, and to compute the output at the present time index, present time t, you require in the argument of the input signal t plus 1. So that is again non-causal. Both the systems are non-causal. So if you require the future inputs, the system is non-causal. But you can also say that even the system, if the system is non-causal, the system also requires memory. Okay, so it has to have some information or storage associated with it. So these are non-causal systems. All memory-less systems are causal. Okay, you see, because since the output responds only to the current value of the input. So if the output is responding to the current value of the input, well then it's a memory-less system. Okay, but over here this is not a memory-less system. This is a system with memory. This is a system with memory. So it's not a general classification. So capacitor, for example, is a system with memory. Similarly, inductance is a system with memory in continuous time electrical systems. So, although causal systems are of great importance, they do not by any means constitute the only system that are of practical significance. For example, causality is not often an essential constraint in applications in which the independent variable is not time, such as in image processing, where the independent variables are space coordinates. So you can have a non-causal image processing with space coordinates. Okay. Then furthermore, in processing of data that have been recorded previously, as often happens with the speech, geophysical, or meteorological signals, to name a few, we are by no means constrained to the causal signal processing. Okay, you can have a non-causal signal processing on the recorded data. So if you have a recorded data, you know what is in the past and what is going to happen in the future. Okay, so that's recorded data. So, for example, geophysicists, they use this data of waves associated, the ground waves, to predict earthquakes, for example. Similarly, Met departments, they use meteorological signals to predict the weather conditions. So these are predictions based on the recordings, right? Similarly, for example, as another example, in many applications, including historical stock market analysis, demographic studies, we may be interested in determining slowly varying trend in the data. It also contains high frequency fluctuations. Okay, so the fluctuations would be sharp. There would be a sharp trend, and you might need to smooth them out. So you can do a running average. So in this case, a commonly used approach is to average the data over interval in order to smooth out these fluctuations. These fluctuations could be sharp fluctuations, so you need to smooth them out. So and keep only the trend. So an example of non-causal averaging system is like this. Okay, so you see your range of vision for this sequence is from k minus m to k plus m, which requires that this summation has to be done. This is an average. Okay, so these are 2m plus 1 samples, so you're doing a running average. This will be starting with xn plus m. Okay, and you're going to add this up plus dot 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 plus up until x of n minus m. Okay, so these are how many samples? These are the length of this samples is capital 2m plus 1 samples, and then you're going to take the average. So you see, you require the future, you require the past as well. This is a non-causal system. This is a non-causal discrete time system. Just to, I mean, this averaging to reduce these fluctuations is you require a non-causal system for that. Okay, but this fluctuation, for example, in a particular stock market analysis and demographic studies, this is again recordings. These are again recorded data, and you are determining slowly the trend in the data, and you have to eliminate these sharp fluctuations. So you have to on recorded data, non-causal signal processing is possible. That's the idea. So, okay, this is an example 1.12 from your course text. So it says when checking the causality of the system, it is important to look carefully at the output relation. So to illustrate some of the issues involved in doing this, let's check the causality of two particular systems. The first system is being defined by y of n equal to x minus n. So is this causal? You see, it's very tempting to say that, okay, if your index, let's consider a certain index n naught, okay, and this y n naught, if I need the output at the discrete time index n naught, where n naught is positive, okay, let me indicate this, where n naught is a positive integer, and the discrete time index is always an integer, okay, it's not a fraction. So n naught, it can be positive, it can be negative. So n naught is a positive integer, the positive quantity. So y naught requires x of minus n naught, which means that if, for example, if you have to evaluate this y at 4, okay, then y of 4, because it's positive, y of 4 will require the sample x minus 4. That is past, okay. So the system seems to be causal at this instant in time, but you see, it's very tempting to just conclude the system to be causal, but that's not the whole story. You have to consider n naught. What happens when n naught? What if n naught is less than 0? So you have to evaluate the system for all the time. What if n naught is less than 0? So for example, if I have to evaluate this at y minus 3, okay, if n naught is less than 0, so if to evaluate y minus 3, I need x3, which is future, okay. So that means for all instances in time, this system is non-causal. The system is simply non-causal. So like it says, note that this output y naught at positive time n naught depends only on the values of the input signal at time minus n0, which is negative and therefore in the past of n naught. So we may be tempted to conclude that at this point the signal is given system is the given system is causal. However, we should always be careful to check the input-output relation for all times. So in particular, for n less than 0, for example, if n is less than 0, n minus 4, then to compute y minus 4, you need x4. So the output at this time depends on the future value of the input, and the system is non-causal. Okay, so you have to check it for all the times. Okay, so for example, over here, if you have to compute the output for negative time index n, then it requires the future samples of the input sequence, which implies non-causality. Okay, and another function that is given to you for a continuous time system is xt cosine t plus 1. So it is also important to distinguish carefully the effects of the input from those of any other functions using the system, using the definition of the system. So for example, over here, x of t is the input. Okay, so let's remember x of t is the input, and you can see that the other function, I mean, you can write this as xt multiplied by some other function, call it gt. Now this gt is not your input, it's just a function. For example, over here it's a cosine function, and it's taking some values. I mean, in the argument you have t plus 1, but this might seem like you require another other sample, but it's not a part of xt. Xt is your input, and in order to compute the instantaneous value of the output, it requires the present time value of the input signal at time t, right? It does not require t plus 1. Okay, so it doesn't require the future from the input. The other function, you see the other function, it's just the value. It doesn't have any importance. So the system is still causal, you see. So in this system, the output at any time t equals the input at the same time multiplied by a number that varies with time. So it's just a number, it's not an input. So the above equation can be written as xt. This is the input. This is important. So if you consider that this system has an input multiplied by another number that is time dependent, so it doesn't implies it has no implication in classifying the system as causal or non-causal. So gt is a time varying function, namely cosine t plus 1. Thus the only current value of the input influences the current value of the output, as we conclude that the system is causal and in fact memoryless. Okay, so it doesn't require any storage, because it's just like a multiplication of the input, the present input, instantaneous input signal by some number which is time dependent. So it is, yes, it is memoryless. Okay, and it is causal. It is causal. It is causal and it's memoryless. But over here, this is non-causal. The discrete time system that we have discussed before, y of n, x minus n, it's non-causal, but it requires memory. It requires memory. So if you have to do such signal processing, it might be if it is a recorded data, then you need some memory. Okay, you need some information storage as well. So this is a system with memory, but it's non-causal. That's all.